was talking about the pilot Torres project, which is a small telescope in Macon, in Cerro Macon. The site has energy and connectivity, has an operation center in a town which is down the mountain. And in the Taurus collaboration, we have agreements with Bosque Alegre and Casleo, Gemini, and the Falcon telescopes that are on Chile, and also with the Abras collaboration, which is a consortium with Brazil and Chile. So while we were developing this pilot project, we received this. This is a circular from the GCN circular system. GCN means gamma ray circular network. And this was a circular from, you can see the date here, September 15. I'm sorry, September 20, 2015. And it basically said that the LIGO pipeline had detected a trigger on engineering mode. This was a few days before the observing run from LIGO. The device was on engineering mode. That means some final adjustments were being made. During the night in the United States, it arrived this signal to the detector, which was actually the first ever detection of a gravitational wave. So this signal was so strong and so good that many people thought at the moment, I remember that clearly, that the signal was actually an injection. There was this procedure when a few people in the LIGO collaboration were allowed to make secretly injections in the system just to check if the system is able to detect a signal of a gravitational wave. It was made several times, and many people thought that this signal was an injection because the signal was so good. We, in the Taurus collaboration, had an agreement with the LIGO collaboration for which we access the data from the detection. And we were asking if this detection was actually a signal or an injection. And actually, people in the LIGO collaboration have many doubts. They thought they had been hacked and that someone had just illegally injected this signal in the device. But the fact is that it is very difficult to obtain this kind of signal making a fake injection. So after several months, LIGO collaboration decided or concluded that this signal was actually a signal from space. So in this circular, we see that there is a web page from the GraceDB, which is a database from the LIGO collaboration, where we can go and download maps, which are Helpix maps, with the probability of the position of the origin of the gravitational wave. LIGO has 4 different pipelines, and each one of these 4 pipelines generates a different map. And the map is something like this. As you remember, we talked a few minutes ago about how difficult it is to spot the right position of the origin of the gravitational wave. So we have a whole region in the sky with a high probability of the occurrence of the event. This region is really very large. You can see, for example, in this cut here, the projection of the probability for the 4 different LIGO pipelines. Right? So the task now is that if we want to search for the electromagnetic counterparts of the gravitational wave, then we need to search for transient events in all these regions of the sky. This is the signal of the this is the first detected gravitational wave signal, which has 3 clearly different parts. The first part is the in-spiral part, where the 2 black holes are getting closer. This is the merger itself, when the 2 black holes are change its shape and form the new black hole. And this is the so-called ring down part, where we have a new black hole instead of 2 black holes, and we have no more gravitational waves from here on. This signal was observed on the both LIGO detectors. This is the signal from Hanford, and this is a signal from Livingston. In fact, the signal arrived at the 2 detectors with a slight difference in time, which is just the time it takes the light to go from one detector to the other, approximately. And we can see here a wavelet reconstruction of the signal, which is intended to filter. It is like a low pass band filter of the data. And we see also the reconstructed signal from templates, because the system works like this. Once a signal arrives to the detector, it is compared to the collection of templates, which are produced by numerical relativity, considering different combinations of masses of 2 compact objects. And then if we compare the signal with all these entries from the collection of templates, we can say what kind of system are we watching at, right? In the bottom, we see these plots. The x-axis is time in seconds. This scale is actually, it is possible to detect it on a human scale, right? It is seconds. And here we have the frequency of the wave. If we translate this frequency to sound frequencies, it is just in the audible region of the human ear. For example, the human voice has 100 or 120 hertz, for example. So we can actually hear this, which is something like whoop, something like this. First, low frequencies, and then high frequencies, and in a time scale which is a fraction of a second. And that's it. That is the signal of the merger of 2 black holes. So after this detection, many telescopes in the world observed the region of the sky. And as you can see, there were many observations of the high probability regions, and nobody found the signal of a strong transient event, which is what was expected, because the model indicated the model here indicated that this signal corresponded to the collision of 2 black holes, which are not supposed to be followed by a signal in electromagnetic waves. This was the first event, but in the observing run of the LIGO, many other events were observed. For example, here we have the first detection incorporating the Virgo detector, the Virgo which was in Italy, which started sometime after the LIGO detectors. So as you can see, the probability region when we have 3 detectors is much lesser in area than the probability region when we have just 2 detectors. Right? That's the reason we it is useful to have many detectors in different parts of the world. And this here is a very important detection here, the event 170817, which was the first detection of a kilonova event. It happened in 2017 on August 17. As you can see here in this catalog of gravitational wave transients, there are 10 events which correspond to the collision of black holes, and we have this one, which, as you can see, is a little bit different. It corresponds to the collision of two neutron stars. Maybe you can see closely the signal here. It took a minute more or less. That is a time frame much larger than the case of the collision of black holes. Let me just skip this. I want to show this, right? This is the signal of the collision of the two neutron stars. And the important thing is that approximately 2 seconds after the merger events, a spike was observed in two gamma ray satellites. So in the same region of the sky. It is very unlikely to have two of these events, a gravitational wave and a gamma ray burst at the same time. So it is an indication, a hint, that these two events could be part of the same event. So with this, it was possible to constrain the region of the sky of the origin of the gravitational wave. We see here the probability region. This curve is the curve that encloses the 90% of the probability of the origin of the gravitational wave. So it is supposed to be in that region with a 90% probability. If we use Virgo detector, then we can constrain better the region. Actually, Virgo did not observe this event, but people at the LIGO-Virgo collaboration assumed that the event was real and it was not observed at Virgo because it should have been observed, because the event was just in the blind spot of the Virgo detector. So this allowed to constrain the region to this smaller area on the sky, And this is the region from the Fermi satellite, and this one in brown is the region from the integral satellite. So finally, a galaxy was found, NGC 4993, where a new object appeared in the image. For example, this is the image taken 10 hours, 11 hours after the merger event. That is 10 hours after this time. Okay, and this is an image taken 20 days before the event. Why 20 days? Because in order to detect transient events, we need reference images. So while we are not observing gravitation, while we are not searching for the electromagnetic counterparts of gravitational waves, we need to make catalogs of the sky. We need to have a catalog of the full sky to compare with the new images to detect transient events. So this is just the detection of the first kilonova. Since we are making new science here, almost everything is the new, or is the first something. the first collision of two black holes, the first detection of a kilonova, the first collision between a black hole and a neutron star, etc. As you can see here, the light from the kilonova goes down very rapidly. In a matter of days, we see that the kilonova disappears in the optical part of the electromagnetic spectrum, and then it starts to appear at larger wavelengths, for example, infrared or radio, which is what is supposed to happen from the kilonova model. As you remember, this is an artistic representation of the kilonova model. This is the plane of the original orbit, and this is the jet, right? So the collision of the jet with the surrounding material produces this glow, which is progressing with time and producing emission at different wavelengths. This is an artistic representation of that. So it is very important, as I said, to have observations of both gravitational waves and electromagnetic observations. But it is not easy because the region of the sky, as you see, is very large. So there are several problems here. First, we have to search in a large region of the sky. Then we have to identify transient objects. It is not possible to do this using traditional methods. For example, if you want to study a galaxy, let's say, you go to the telescope, you take the images, then you retrieve the images from the observers, you sit at your desk in your computer, make the reductions of the image, and then study the image. It takes several days or months even to do this. But here, since the kilonova disappears in a few days, we have to do all this process in just a matter of hours and for a very large region of the sky. So we require an automation, and we need to make an automatic reduction of the images and an automatic detection of transient events. Well, this is the Taurus dome. This is a photo of a few days ago. This is the telescope of the final Taurus project, which has been installed. It has not seen first light yet because of the coronavirus pandemic. So with Taurus, we aim at producing a survey of galaxies for reference imaging, and use this reference imaging to make the following up of gravitational wave alerts, to develop automatic data reduction pipelines, to develop skills on austrostatistics and astroinformatics, and also the engineering required for the automation of the dome, and making progress in big data and machine learning. These are the science cases for this project. Regarding the pipeline, we need to make an intelligent agent that is able to receive the images taken by telescope, make the reduction automatically, and then detect transient candidates. Right? Let's see how we do this. The process is the following. We have the reference image, and then we have a new image. This is supposed to be a new image in the region of the sky where we are looking for the electromagnetic counterparts of the gravitational wave event. So we make a difference between these two images. The difference is not a process that you just take the reference image and make the subtraction with the new image, like a difference of two matrices. and obtain a new image. It's a little bit more complicated than that. The reference image usually has a much better quality than the new image. And even it can be taken with a different telescope on different conditions. So there are many artifacts in the image. For example, the bleeding of the images, the coffee stains, the different dark and bias, and so on. So if we make this difference without taking care of these effects, then we will detect many places where we have a strong difference between the two images that are not necessarily the transient events. So basically, we are doing this. We have the reference image. We make a convolution with the kernel function, and we are supposed to obtain the new image. Then the kernel function contains the signal for the transient event. Okay? Well, there are several methods to do this. We used in our work these 4 methods, which are I'm going to explain quickly now. So the Sakai method considers a pixel-based hypothesis testing. It is a statistical procedure to say if a given pixel has a given probability of being different in the new image and in the reference image. The Bramich method uses a convolution with a kernel function, which is decomposed into base functions, in a series of base functions. So we can use just the first terms and obtain an approximation. And in this method, the kernel is assumed to be the combination of delta functions. That is, a delta is a spike in the image where the transient event is supposed to be. The hot pants method is an implementation of the hot pants software, is an implementation of the Allard-Lupton method, which proposes this function, which is a cost function. We basically have a minimization problem to search for the kernel that gives the less cost in the cost function. And finally, we have the S-core method, which uses a convolution of the reference image with the PSF, right? And this is very useful because if we, for example, use a reference image taken with one telescope and seeing conditions and all the observing conditions, and try to compare it with a new image which has been taken with very different conditions, for example, different PSF, then the difference will produce many artifacts, right? So this is, with this method, we are trying to disentangle the PSF from the image. Here we have examples of this procedure. The new image, the reference image, these are simulations, right? And the results from S-core and Allard-Lupton, for example. I am going to talk more about this in a few moments. And these are examples of difference imaging in a galaxy which has a transient event, in this case are supernovae. So as you can see, the task objective is to make the galaxy disappear and to highlight the point-like event, which is the transient event. So in order to do this at large scale for many images, we need to train an intelligent agent that makes all this process automatically. So we need a different approach than the traditional paradigm. In the traditional paradigm, we have a code, we read data, we put it in a computer, and we obtain the results. In this paradigm, we use models, we use statistics, numerical methods, high-performance computing, and it is possible to make an interpretation of the results because we just program models and use statistics in the code. Another approach, which is the machine learning approach, is somewhat different. We have data and we have results. With the data and the results, we teach a computer how to generate a code, and then we use this code with new data. So in this case, we have also models, we use statistics, we use numerical methods, high-performance computing, but also we need computing architectures or better software architectures that are trained and that are the new code generated by the training. And the most important thing is that we need training data. For example, let's suppose that we have many pictures, and in some of these pictures we have cats, right? Little cats. So we can use these images to teach a computer that some images contain cats and some other images do not, right? So we need many images, some with cats and some without cats, to teach a program how to recognize an image that includes a cat, right? If we do this, then we're creating a code that is able to identify cats in images. But if there are some problems. For example, if we use an image with a tiger, it is possible that the program trained with pictures of cats recognize the tiger as a cat, okay? So there are some limitations. The most important thing here is to have a training, to have available data for the training of the code. So let's see quickly how this works. We use, for example, there are many more, but I am going to show you three architectures, that is three methods of machine learning to make a classification. See, this is the problem of classification. We have to classify the pixels on the image, which are background or signal, right? The signal will be the transient event. From the image, we obtain many characteristics or features or parameters. And in this parameter space, which in general is multidimensional, we need to separate the features that correspond to a positive detection, that is a transient event, and the features that correspond to noise, background noise. We can do this obtaining a linear function that separates with an hyperplane in the hyperspace of the parameters the two classes of objects. This is one strategy. Another strategy is the k-nearest neighbors, which consists in the following. Suppose that we have in the parameter space the two types of observations, the signals and the background, and then we have a new observation, a new data, right? So we can consider a hypersphere around this new data and watch how many occurrences of one class and another class can we find in this region. So it's like a voting system. So if we have more instances of a positive class, then we assign a positive class to this new observation. I will try to be more clear just in a minute. And the final architecture is the random forest, which is composed of decision trees. A decision tree is a computing structure where we use the data to identify the parameters that separate better our data in the two classes of interest. Making slight variations in these decision trees, which are random variations, we can make many instances of these decision trees. And finally, we have this set of trees, which is called the random forest. And with the voting system, we again can give probability for a given observation to be a detection that is a positive or negative. In a classification problem, which is binary, which is our case, because in an image, we have an object, right? And this object can be a transient event or an artifact from the image. So we need to classify this. It is clear the idea? Let me ask you.
Yes.
Clear? Perfect. Right. So we have to make metrics to decide if our classification is made right. Okay. So we have these four concepts: the true positives, the false positives, the true negatives, and the false negatives. This come from the so-called confusion matrix. This matrix is the following. We have in the training sample, that is in a sample where we know exactly if a given detection is positive or negative, and then we construct using a given architecture an intelligent agent able to classify that can be mistaken sometimes. So we have to compare the actual classification with the predicted classification. If we put in the algorithm a positive observation and the algorithm identifies it as positive, then we have a true positive. Similarly, we have a true negative when the classification is right. But the classifier can make mistakes. For example, it can classify as negative a positive event, or as positive a negative event. So what we want is that we have a large number of true positives and true negatives, and a small number of false negatives and false positives. Okay, so using these quantities, we construct metrics from the machine learning procedure. Mainly the recall or true positive rate or sensitivity, which is the fraction of observations which are actually positive, which are identified by the algorithm as positive. Okay, and then we have the precision or purity. These are two names for the same thing, which is the fraction of observations that are classified by the algorithm as positive, which are actually positive. Is that clear?
Yes, yes.
Okay, perfect. And then we have other metrics, for example, the F1 score, which is an harmonic mean of the precision and sensitivity. This is the precision and this is the sensitivity. And we have also the accuracy, which is the fraction of the total number of observations that are correctly classified. That is the true positives and the true negatives divided the full set of observations, right? So what we want is that the area of the true positives is large and the area of the false positives is small. And then the area of the false negatives is also small, and the area of the true negatives is small. Okay? Now, there is a balance between these things. Let's see this example. Suppose we have positive and negative events, right? White is positive and gray is negative. Okay? It means that we know for sure that these events are positive or negative. And then we construct a classifier that puts a threshold here. See, we have to make a decision because as we see a minute ago, most of the algorithms assign a given probability of an object of being to a given class. Okay, for example, let's think that we are trying to decide if a given spike in an image is a real transient or an artifact of the image, produced by, for example, defects, change in the DSF, or coffee stains, or bleeding, or something, right? Our algorithm assigns a given probability of this observation of being a positive observation. But we have to decide what observations are we keeping. The ones that have more than 99% of being positive, or the ones that have more than 70% of being positive. We have to make a decision. Okay. So if we shift this threshold to the right, then we will arrive at a situation where all the positive detections are actually positive, right? We have a small contamination, but we are losing many observations also, right? So we have a low purity. If we shift the threshold to the left, then we, for example here, then we will be sure that all the negatives are actually negatives, right? But there are also some negative detections that we are considering as positives. Okay, so it is not possible to have a high purity and a low contamination at the same time. Do I explain myself? Perfect. You're very clever. Well, there are two traditional visualizations of this situation. One is this plot, which is called the ROC curve, which means receiving operand curve, where we plot the false positive rate, FPR, false positive rate, and the true positive rate.
Sorry, Marcelo?
Yes. Yes.
If we can end meeting and enter again to the link, please. It's 15
Okay. Okay.
seconds left.
I promise this is the last time.
Okay, see you.